So that was the solubility of solids in water. You increase the temperature and the solubility goes up. Gases behave a little differently. And solutions of gases in water are very common. The tap water has a number of dissolved gases in it. Temperature affects gases more in a different way. The solubility of gases decreases in liquids. And that's the opposite of what happens with solids. We know this on a everyday level because I think everyone recognizes that warm soda is going to go flat faster than cold soda, right? And you could try that at home if you don't believe me. You take 2 cups of soda, put one in the fridge, leave one on the counter, and taste them periodically and see which one goes flat. The warm one will go flat faster. This also is important in terms of oxygen levels in lakes or in the aquarium in your house or in the river where a factory is dumping clean but warm wastewater into the river. At higher temperatures, there's less oxygen in the water. When we first moved to the Central Valley, the kids went to, actually it was the Ridley Fiesta, and they got a goldfish, right? And then, the kid got the goldfish. Now we have to provide for this goldfish. Well, it was warm in the house, right? And goldfish are cold water fish. And so this goldfish is always at the surface kind of gasping for air. So I did some research. And yeah, they want the temperature to be more like 72 or something. And the solubility of oxygen is higher. I'm like, I am not running the air conditioner all summer long to keep the house cool for this goldfish. Well, it turns out they will adapt after a while. So we gave him a few ice cubes for a while. But eventually he got used to it and lived a nice long life. But if you take a fish from a cold water lake and throw it into a lake with warmer water, it will probably die because it's not used to the different levels of oxygen. And so fish are very sensitive to the temperature of the water in which they live. Pressure also has an effect on the solubility of gases. It doesn't really affect the solubility of solids in water, but it does affect the solubility of gases. The solubility of a gas will increase with the pressure of that particular gas above the liquid. The more gas that is in that region above the liquid, the more soluble that gas will be. Like how this so much relates to soda. So here's a can of soda. There's always a little bit of airspace in the soda, and that contains carbon dioxide under pressure. The high pressure of carbon dioxide there causes more carbon dioxide to dissolve into the soda. When you release that pressure, that's when you start to see bubbles coming up. You can't see it in a can, but if you open a 2-liter bottle of soda, you start to see bubbles floating up, right? Why didn't it do that before? Because they couldn't go anywhere. And now they can get out. And so as soon as you release that pressure, the carbon dioxide begins to come out of solution because the solubility of CO2 in the water is less. If we increase the pressure, so here we have a situation where we have an equilibrium between carbon dioxide in the gas state and dissolved in water. The rate of carbon dioxide coming out of solution and going back in is the same. If we press down on this, if we decrease the volume, we're increasing the pressure of the carbon dioxide. The carbon dioxide going into the water is going to depend on the concentration or pressure of carbon dioxide in the gas state. So if we increase that, we cause more CO2 to dissolve in the water. And eventually it will reach an equilibrium where the solubility is greater than it was before. You'll get a new equilibrium established. Any questions? Yes?
So for solids, the solubility is proportional to temperature?
It's not proportional, but it is temperature dependent. Mm-hmm.
Here for pressure for gas.
Well, it is pressure dependent, it is also temperature dependent. But the temperature dependence is the reverse. For most solids, higher temperature, more soluble. For gases, higher temperature, lower solubility. Now, they used to sell these things to, help your soda stay fizzy longer in the 2-liter bottle. And they would pump air in there. Well, pumping air in here, there's a little bit of CO2 in air, but it's like 1% maybe, very small amount of CO2 in air. It's the pressure of the gas that you're interested in that matters, not the general pressure. So if you use one of those things for wine that pumps CO2 into the bottle, that will keep your soda longer. But if it's pumping air in, it's not going to work. So there is an equation that describes the relationship between gas solubility and the partial pressure of that gas. And it's called Henry's law. So Henry's law, S equals KHP. So S is the solubility of the gas. It's usually described in moles per liter. KH is the Henry's law constant. And that's going to be different for different gases, different solvents, different temperatures. And then P, gas, is the partial pressure of the gas. And usually that's in atmospheres. It depends on what the units on Henry's law constant are. So here's from your book. There's actually a mistake in your textbook. It's 3.7 times 10 to the minus 4, not plus 4. So for these different gases, this is for water at 25 degrees Celsius. These are the Henry's law constants. And here it's molarity, moles per liter, per atmosphere. So you would want to use the pressure of the gas in atmospheres. So determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1.0 atmospheres. Assume a partial pressure for oxygen of 0.21 atmospheres. We're going to need the Henry's law constant, so let's go back. Oxygen, right? 1.3 times 10 to the minus third. So KH equals Is that right? Okay. My short-term memory is, I don't remember what happened to it. The pressure that we want is the pressure of the gas we're interested in, oxygen. So this is the pressure we want. The pressure is going to be 0.21 atmospheres. It's not the total pressure, it's the partial pressure. So the solubility is going to equal KH times P. So 1.3 times 10 to the minus third moles per liter per atmosphere times 0.21 atmospheres. So the solubility of oxygen in water under those conditions is 2.73 times 10 to the minus 4. We should round that to 2 sig figs. 2.7 times 10 to the minus 4th moles per liter. Any questions? Henry's law is important in medicine because if you think about giving someone anesthesia or if they have various issues with the oxygen saturation of their blood, You can increase the solubility of oxygen in a person's blood by giving them a higher amount of oxygen in the air that they're breathing. It's dependent on the partial pressure of the oxygen, not on the total pressure. So you don't have to pressurize the person. You just have to change the partial pressure of air, of the oxygen in the air.